Welcome. It's great to have you all here with us. You know, a lot of us are really looking forward to Thanksgiving, and it's a great time to cook a lot of food. Some bad news, my wife doesn't let me help with the cooking anymore. This may be a case where you can get too into math. You know, I like math, but she asked me last year, why did you turn the oven over? I said, that's because the instructions said put the turkey in at 180 degrees. And, okay, someone who knows math will explain that to you. If you get to geometry, eventually, okay. All right, well, a little bit of science news. German researchers have created a new metal complex built from manganese. And this new complex of metal that they've created has some very special properties when it comes to being able to potentially split something like water. Their ultimate goal with this research is to create a material that, when paired with another material that they're still working on locating, will be able to split water into hydrogen and oxygen without having electricity. So imagine a little rooftop unit with the sun shining on it, some water coming in, and just out comes hydrogen. Wouldn't that be a neat way to add some hydrogen power to your home? And that's what we're hoping maybe they'll be able to develop. So stay tuned for more exciting research. Well, it's time to get it over to Dr. Joshua for How to Study with Acellus Gold.
We received some great questions from students and parents about how to meet the attendance requirement for Science Live for the Roger Billings Scholarship. And we want to take just a moment to talk about some of the questions that we received. One of the questions that's come in from students is, how can I make sure that I'm attending Science Live in a way that will count toward the scholarship? And it turns out there are two different ways that you can attend. The first is to sign into your Acellus student account and to look for the Learning Activities section. When you click on Activities, you're going to find a section called Science Live, and if you select that, the system will automatically sign you in so that it logs that you attended Science Live that week. If you look in the top right corner, you'll see that the system has already signed you in and your name is listed there. The other way that you can attend is if you go directly to the website sciencelive.com. Maybe if you want to put it up on the big TV screen or something, but you have to remember, if you go to the website, to sign in. There's a little button in the top right corner that says sign in with Acellus, and you want to make sure that you select that button and put in your Acellus ID and your password so that it acknowledges and logs that you attended Science Live. And we've been working on making it so that you'll be able to receive a science credit as you participate in Science Live in a class, and so that's something exciting that's up and coming. If you're on the website, I just want to point out that if you click that Post a Comment button, it will automatically take you to the latest episode of Science Live, and you can see all the comments posted by other students, and you can submit a comment as well. So question number 2 is, do we need to watch the broadcast live? And we highly encourage you to tune in live, but for the purposes of meeting the scholarship requirement, you can tune in later during the week and watch the recorded episode. As long as you sign in sometime during the week, it will record that you've met the scholarship requirement for that week. So what happens if you miss one episode? Do you automatically lose the scholarship? And the goal of these sessions is to really encourage kids to see the value in education and to study hard. And so we encourage students to attend at least 75% of the time for the purposes of meeting the scholarship. And as we get to the point of rolling out the 4-credit class, one of the things that fortunately we'll have to do is look at the students who aren't meeting that. But as long as your student is consistently meeting 75% or more, they will be able to maintain and continue to receive the scholarship, which raises the question, so as a parent, how can I see if my student has watched? And if you sign into your parent account, in the bottom right-hand corner, there is a button that says Learning Activities. If you click on this button, you'll see all the different learning activities that your student has completed. And if you see Science Live listed as one of the learning activities, that means that the system has recorded that your student has attended. And you can see a timestamp on the right-hand side. So this is a quick and an easy way for parents to verify that their student has signed in and logged that they attended. And speaking of learning activities, there are so many exciting things that students can explore. Remember, the learning activities are locked up, except for Science Lab. You can access that anytime. But the other activities are locked up until the student completes their daily goals. And there are so many exciting learning activities. One activity called Write a Book allows you to use your imagination to weave a story, creating your own characters. And to tell us all about it is one of our very own Acela students. Take a look.
Hi, my name is Wayne, and I just finished my goals for the day. Now I get to do my learning activities. Let's write a book. First, we need to create a cover. Let's write one about socks. Dirty socks. Timmy lost his dirty socks. Where could his socks be? Mom said it's time for a bath. Go find your dirty socks. Timmy ran to the barnyard to ask the animals. Cow, have you seen my socks? No, said the cow. Pig, have you seen socks anywhere? Nope, said the pig. Hen, have you seen socks around? Cluck, not me, said Hen. Then came a happy sound. Bark, bark. Timmy finally found his dog named Socks. There you are, Socks. Ready for a bath? Said Timmy. The end. Bye.
We'll be sure to check out those learning activities. Let's hear it for Wayne.
Well, it's time to get it over to Dr. John for the Technology Spotlight.
Did you know that some jets can go faster than the speed of sound? It's amazing. They call it supersonic flight, but not as many as there could be. And one of the reasons is that it's actually illegal to accelerate to the speed of sound over land. And a lot of flights go over land. And the reason why is because as you go faster and faster and go faster than the speed of sound, there's what they call the sonic boom. There's this loud boom that is so loud that it's disturbing to people on the ground. So they made it illegal. Well, NASA has been working on this. They have a new test jet that they call the X-59. And the point of this jet is to learn more about how to reduce that sonic boom. And they just barely did a test flight. I want to show you a little video of it. All right, here is the X-59 pulling out for its first test flight. You might notice that it has a really, really long nose. Look how long that nose is. And it's not just to be funny or anything like that. There's a real reason. And of course, it's to reduce that sonic boom. And the idea here is to spread out the noise so there's not one big boom, it's more spread out, but also to reduce it. And they've been studying this in the wind tunnel and in simulations a whole bunch for quite a few years. Here's an illustration of the simulation, and those lines you see coming off the shape of the jet are where there's the most noise. And you might notice if you look carefully that the lines are darker and more pronounced on the top of the jet. And one of the things they've realized is that if there's a loud noise going up, no one's going to hear it on the ground. And so they've been trying to figure out how to do that. For example, they put the jet engine positioned just right so most of the noise goes up instead of down. And then, of course, that really long nose makes it so the really loud noise right at the tip is a lot less. And then the shape of the wings and the tail are positioned right so the noise is spread out a little more. And so they've been simulating and testing their ideas in the wind tunnel, but it's finally time to do a real flight. So I want to show you the aircraft going over to the runway and taking off. Here we go. Notice the engine up on top to block that noise. There it goes. Now, there's a problem with having a really long nose like that. And the problem is the pilot can't see. And some of you might remember back when they made the Concorde jets, remember these are the passenger jets that can carry people, they had the same problem because it had to have a really long pointy nose to be more aerodynamic. And then when it's time to land, the pilots wouldn't be able to see. So they came up with this idea that the nose on the Concorde could bend down. Here's a picture of the Concorde during takeoff and landing, and you'll notice how the nose is bent way down. It looks kind of funny, doesn't it? But that makes it so the pilots can see, and then as they get up to altitude, they speed up, they straighten up the nose, and they can go supersonic. Well, instead of doing that, with this one, that would be a really long nose to bend down. Instead of doing that, they have no front windshield on the X-59. So the pilot can't see out, except they have HD cameras, and they make a wraparound screen view inside the cockpit. So the pilot sees something more like this. And so it's just a screen, and they've got information about, you know, how fast it's going and how high it is and everything on the screen there. And then the pilot can actually see more than usual because you can see under the aircraft too, because it's HD cameras making the view. So I want to show you a little video. Here is real footage of the pilot landing. This is what he sees, and this is what it looks like. And it's tipped way up like that, and he wouldn't be able to see anything except those HD cameras are showing him exactly what's happening. Coming in for a perfect landing. There we go. The first real landing of the X-59. Really exciting. Now, during this flight, they didn't really go test how well the sonic boom is reduced. Instead, it was just like a practice flight. They didn't even retract the landing gear. They kept it out just in case. They went up to 12,000 feet and they sped it up to 230 miles an hour. And of course, the speed of sound is more like 600 miles an hour at that altitude. And so this was just a little test drive. And here is footage of the pilot coming back successful. And it's Nils Larsen. Wouldn't it be cool to be a NASA test pilot? Really cool. Oh, yeah, a little celebration going on there. But it's really, really exciting to see this starting to happen. And pretty soon, we're going to find out how well it actually works in the real world. And the idea is instead of a sonic boom, it'll be more of a sonic thud, you know. Booms aren't legal, but what about thuds? All right, we'll have to look into that. And they think the sound is going to be about as loud as someone closing a car door outside when you're inside a house. So you can imagine that. That's a lot quieter than what it is right now. So maybe someday we'll all be going a lot faster. That's all the tech we have the time for. Thank you.
Now it's time for Breakthrough Moments in Science with Tobias.
Well, we're going to talk about a battery and a certain kind of battery, but to appreciate the battery we're going to talk about, we've got to start hundreds of years ago, and we're going to quickly breeze through the jar, the Leyden jar, okay? Now, the Leyden jar is, if you look at this picture, it's a discovery that was made in the 1700s, and it was by a scientist that was in the city of Leyden in Europe, okay? And so that's why it was called the Leyden jar. And this jar experiment that he did, he was basically holding this glass container and it had liquid in it, water or salt water, sometimes alcohol. And then he had a metal rod, kind of like a long nail, going through a lid into the liquid, and it was sticking out the top, okay? And then he had a static electricity machine. And static electricity was kind of the electricity of the time. And they kind of thought of it as this magical liquid or flame, and we didn't know very much about electricity. So he's doing this experiment where he had a static electricity machine that generated static electricity, and he held the metal part that was sticking out of the jar near this machine, and he charges the jar, or as he termed it, he filled the jar with electric liquid. Okay? But his story was he filled it up, he's holding the jar, and then he touched it. And when he touched it, there was a pop sound, and he actually saw a spark, we would call a spark, between his finger and the point that was sticking out of the jar. And when he started to spread this news, scientists around Europe were super excited. Everybody was trying to make their own Leyden jars. And the way you would measure how good your jar worked is how big was the zap. And if you had a big zap and it actually hurt a little, it was like, whoa, how'd you do it? And so everybody was trying this out and making their version of the Leyden jar, but no one could figure out how it worked. And all across Europe, people were writing about it. And finally, a scientist from the New World, Benjamin Franklin, would get his hands on a Leyden jar. And he wrote, when I got this latest, one of his friends in Europe sent him one. And he said that when he got this, he basically couldn't think of anything else. He was so excited because he wanted to do experiments with this Leyden jar. And so he starts recreating the things other people had done. But of course, this is Ben Franklin. So he takes it a step further, and he starts putting, how do you make the zap stronger? A bigger jar? It turns out more jars. So Ben Franklin put together more jars, and when he put more together, more Leyden jars, he said it reminded him of a battery of artillery, like a bunch of cannons. I've got my battery of Leyden jars. And so he started calling them electrical batteries. And that's where the name came from. And since when Franklin named something, it kind of sticks, okay? So he had these battery of Leyden jars, and he started doing experiments. He could get a bigger zap than anybody had gotten so far. In fact, I mean, it's almost Thanksgiving. He actually tried to cook a turkey with this. I would not suggest such a thing. But he actually got hurt really bad because he made a little slip up, and all it took was one wrong touch, and he completed a circuit, and he got zapped pretty bad, quite badly actually. And he created principles or named certain principles of this phenomena that we still use today, like negative charge, positive charge. And he found that there was an indifference of positive charge and negative charge on the inside of the bottle and the outside. And when you touch the top and you were holding the jar, you would complete that path, and the difference of positive and negative that had gotten so large would level out. And that's what was happening. Now, we're going to jump from that to eventually an actual, more of what we know as a battery, the voltaic pile. And we're not going to get too deep into this, but this is basically now creating that difference in positive and negative through a chemical reaction instead of just static electricity, okay? So we have what's starting to look more like a battery. It's kind of like a tall, skinny battery, okay? And then jump into the mid-1900s, and you start getting batteries like this. So this is starting to look a little more familiar. We're used to those batteries that have the top, the positive and the negative on the top and the bottom. This one has both on the top, okay? But if we were to cut these batteries in half, we wouldn't see wet pieces on top of each other. In this case, they call it a dry cell battery. And the chemicals inside are like this dry putty. And you can see that blue part in there is to signify this rod. Usually it's something like copper, a certain kind of metal inside. And basically you have one chemical on the inside and then another chemical on the outside of that chemical. And if they get to mix, they will react. And one of the one on the inside has a much stronger negative electric charge, and the one on the outside has a positive electric charge. So there's an indifference, kind of like when that Leyden jar is charged up, and if they mix together and react, it'll balance. But the battery has a layer of insulation between the two, so they can't get to each other. They can't balance out. So the potential of the indifference of the negative charge and the positive charge is there wanting to make the electrons flow and balance, but they can't. And so that's kind of the point with the battery, is then you make a path, hopefully it's not you, but you make a path for those electrons to balance out, run it through a light bulb, the light bulb comes on, okay? So we start to see in the 1950s all kinds of batteries. And, you know, you got we know now AAAs, AA's, they even had quadruple A's. And the thing is, there's different voltages of them. And if you have like a AA or a big D battery, the voltage of both of those is still under 2 volts. And, you know, you can think of voltage as like the pressure of pushing those electrons. So like if you have a container of water, you fill it up more and more and more, and you have a little hole in the bottom, the pressure's growing. Or if you think of like holding up liquid, and you're going to pour it down a slide. If it's this from here to here, compared to if you raise this side, the voltage, it's going up. So 1.5 volts, that's not too much, right? Well, there started to be a new need for a new kind of battery. And the need was a transistor radio was invented. And so all of a sudden, there was a radio that could fit in your pocket through these transistors, and they needed a battery. They needed a new kind of battery, and they wanted a battery that would be like about 10 volts. Now, there were some that were like 90 volts, crazy stuff that were used in certain areas, not for your transistor radio. But they wanted a battery that was about 10, didn't need to be over 10 volts. They wanted it to be reliable. They wanted it to fit in a little space so it could fit in the transistor radio so you can still fit it in your pocket. So if you're a battery company and you see the need, you've got to figure out as quick as you can and as professional as you can, how do we get a battery made for that? So Everready jumped on this, and they put together a battery of batteries. You can think of Ben Franklin's Leyden jar battery, where he put a bunch of them together in the series, Well, Everready did the same thing with quadruple A batteries. So quadruple, these are like 1.5 volt batteries, okay? And they're tiny. They're really skinny. And they took 6 of them, and they connected them together. Then they made a really tight container, and then they worked with another company. They said, we need a way to connect this into the transistor radio in such a way that it cannot be put in backwards. Because if you put it in backwards, bad things could happen. So we need a connector that you can only do one direction. And if you put it in the other way, it won't connect. And so here's the connector that they got. So if you look, this is starting to look familiar. You have these skinny batteries all set in the series underneath this special new funny-looking connector. And of course, we know what it's becoming, right? Well, it would become, so think about it. You got 6 1.5 volt little batteries, 9 volts that they make together. And the 9 volt battery comes out. And this would be the first battery for this new radio technology that would kind of go with the transistor. In fact, they actually called it for quite some time the transistor radio battery, or the TR battery. And the first transistor radio to use the 9 volt was from the company that Bill Lear, Dr. Billings' mentor, helped to start. Motorola did the first transistor radio. And if you look there, this is the small, pocket-sized electronic. And look at that. See that base thing? It flips up. It's a handle. And this had the new battery inside. And then from there, it just took off. And eventually, they even made some standards, and multiple companies started creating it. And now we have what we all know today. We don't call it the transistor radio. It's just the 9 volt or the touch it to your tongue battery. But if you have a little device and it's electronic and you have a battery in there, just think of that. There's a little system in there. Of course, it's evolved way past what 9 volts are now with the new batteries, but it's still that point of the difference of the 2 different charges, and they want to balance. And we use them wanting to balance to do work for us before they get balanced out. So always appreciate the power in your devices, but please find another way to cook your turkey. All right, thank you.
All right. Well, it's time for me to introduce the father of hydrogen technology, Dr. Roger Billings. Speaking of producing hydrogen from water, he developed the Billings hydrogen electrolyzer, which is a really great way to produce hydrogen at pressure. And this unique design is able to produce that hydrogen at pressure without having to have a separate compressor that wastes some of the energy that you're trying to create. And it's become one that many have looked at in advancing creating hydrogen on site. And a lot of really neat hydrogen innovations that are coming. You kind of have to do something like that when you're producing a new hydrogen car and a new bus and a hydrogen home like he does. Please welcome Dr. Roger Billings.
Et tu, Brutu.
Oh my. What is it for?
It's a water pipe. It's for water.
But why is it on your table?
Good question. You didn't put it here?
I surely didn't.
It's a mystery.
Well, you solve mysteries.
How is everybody doing? It's pretty we learned about Leyden jars.
Yes.
Yeah. You know, I went to school with Ben Franklin. Not quite. But I do remember in elementary school, I remember very, very well the day that one of the students came to school with a 2-transistor radio.
Oh, yeah?
And it was mind-boggling. How could you have a radio that played without being plugged in?
Did you have to check it out? Were you his best friend?
I was just, after that I was. But it was one of those things you couldn't hardly believe. It's kind of like when we made the first personal computer back in 1977, what if someone had come out with an iPhone? Say, hey, what about this? What about this?
Yeah, right.
Just like a million times more powerful and so little, and it's impossible.
It is.
So some of the students have been asking, so how do you make these inventions?
Yes.
And they ask some of the inventions that I've been involved in, how do they come about? And we're on a multi-episode adventure to discover how to make inventions, right?
That's right.
And these things that we've been talking about, like this transistor radio and the 9-volt battery, those were inventions that were made. And it's interesting that Tobias started out with a Leyden jar because that's really kind of how the battery started. And it's a very interesting story, step by step by step. So they made the Leyden jar over in the city of Leyden, okay? And then some good friend, Ben Franklin, shipped him one, and he got it. Boy, that friend did something for the world, didn't they?
He surely did.
Because here's Ben Franklin, and he's got a Leyden jar, and he started figuring out all kinds of things. How do you get a bigger bark? Ooh, ah.
You going to tune to our frequency?
R1.
World.
How do you get a bigger spark? And so he started hooking them in series, like a battery of guns, and that's why we call them battery.
I
Isn't
didn't
it
know
interesting? And he invented positive and negative as a way of describing it. And it's interesting. A lot of us wonder why electricity goes backwards. When you put a battery in a flashlight and turn it on, the electricity goes from negative to positive. And it was because Ben Franklin didn't have a way to see which way it was going, so he guessed. It goes from positive to negative. But what he didn't realize is that the electrons that flow are negatively charged, so it actually goes from negative to positive. The electrons. That was
That's my
not social.
That's my kind of science right there.
My kind of science. Anyway, I think it's really
It's
exciting.
amazing. Yeah.
So we're going to talk about how the inventive process takes place.
Okay.
And I think the big surprise that people need to learn is that there are very small steps.
Right.
And when you break it into small steps, they're doable. If you are in a basement and you want to get upstairs, and when they built the basement, they forgot to put steps in, it's a real challenge to get out.
It is.
But if you have a stairway, then you can just go up one step at a time and you can get upstairs. Well, that's how invention takes place. So let's go back to this Leyden jar. The Leyden jar would take on a charge. Now, they didn't have a generator yet because no one had invented it. So instead, they did the method of rubbing the balloon on the hair, you know, the static electricity build up. But the Leyden jar would store the power. It would store the charge. And so it was kind of like the first battery. For you guys that are a little techie, it's more like saying the first capacitor. And you remember what a capacitor is? It's a cheap battery, right? Capacitors are where you have two plates, and in between them, two conducting plates like a metal. Between them is an insulator, and you power them up with electricity, and one side becomes very positive and one side negative, and it stores up that electricity. Now, it's not like a battery because it really doesn't store that much electricity, just charge on two plates. But when you discharge it, it comes out very quickly. When we're firing something very big, like a big high-powered laser, and we need a lot of power, or the tokamak experiment, we charge up big capacitors because when we discharge them, we can get all that power out instantaneously. So anyway, back to Leyden jars. They had a battery or a capacitor they would charge up, and then you could use your finger, shock yourself to discharge it. Now, we were talking last time about being able to send a message to someone at a distance.
Right.
And remember, we talked about the telegraph where they ran wires. In fact, ran one wire over the pole, and the other wire they used the earth as the conductor. And they would be able to send electrons and get them back through the earth, and it would power a buzzer so we could have long pulses, short pulses, and so Morse code, they were able to send messages. Well, we talked about, wouldn't it be wonderful if we could get rid of the wires? Because then we could send messages more places. We wouldn't have to put up all the wires. And of course, the big dream was, what if we could send a message clear across the ocean?
Right.
It's kind of hard to run a wire across the top of the ocean.
It kind of is.
Nowadays, we run fibers under the ocean, which we send data through by light pulses. But that was the dream. And they couldn't do that in one step, so they had to take tiny, tiny, tiny steps. So some people had theorized that there was a thing called radio waves. And these were waves that would be generated, and they would travel out through the universe, through space, through the Earth's atmosphere. Sound is a wave that's caused by pressure pushing the air against the other air. Water waves are made by pushing water against the water. So if the water goes up, it's got to come back down, which pushes the other plane up, and it propagates a wave. Well, if you could do it with a radio wave, they've theorized it could go a longer distance. But so how do we do it? And one of the very earliest experiments of creating a radio system was the Leyden jar, because the Leyden jar was a source of storing electricity. So they'd charge up the jar, and then they would make a radio wave, and the radio wave could be just from a little spark. And when there is a spark, it creates a radio wave. And what if you could detect the radio wave at a distance? And we actually are going to take an adventure where we try to do just that. We're going to try to create a radio wave and see if we can detect it at a distance. Now, this is the way that they did it. They took the Leyden jar and they hooked a wire from it to a bottle. We're going to use a beaker for our experiment, but a bottle or a cup, a glass cup, in which they had little balls. For our experiment, we're gonna make our own balls, our own little balls out of aluminum foil.
Okay.
So we make these little teeny aluminum foil balls. We're going to put them in this cup, and then we're going to have a wire coming in on one side and a wire going out the other side. And the question is, can we send a radio wave and use this bottle of jars, or jar of bottles?
Jar of balls? Balls?
I've got jarbles in my head.
You're so fun. You're
This
fun.
bottle of little balls in here, we're going to see if we can use it like a switch, so that when there's a radio wave, it lets the electricity go through, and it could run the buzzer or whatever we want to run. And when there's no radio wave, it doesn't.
I'm going to use that. I got some jarbles in my head. I am going to use that.
She fixates on my mistakes. That is not
it's
social.
That's something I wanted to
That
own.
is not social.
Because I do that all the time.
Yeah.
Okay.
All right, but just think, what if we could do that? If there was a way we could detect a radio wave.
That'd be amazing.
And so we need to make a radio wave with one of the very earliest transmitters, which is a spark. So we're going to get a little spark thing, a little spark maker, and we're going to see if we can detect the radio wave by letting the power run through our bottle of homemade aluminum foil balls.
How fun.
What do you think?
You're going to take us on that adventure, all of us?
That will be an adventure.
Okay.
And by the way, that is the very way that the very, very first messages were able to be sent by radio. So we're going to kind of come up through it. How hard is it to take little balls and make them into tinfoil and put them in a bottle? Did you hear that noise? That was a sound effect.
We're just so excited
We're
tonight.
on a roll today, aren't we?
We are.
Yeah. Mm-hmm. So it is really exciting. So Inventioneering is the art of inventing. And I like to call it an art. We have a thing called art, we have a thing called science. When I was in high school, my sophomore year, I won the local science fair, and one of the prizes was from the United States Navy. And their prize was I got to go on a Navy science cruise.
So what is a cruise?
A Navy science cruise. Well, that's what ships do. They cruise.
Okay. So
Okay,
it was
and
a
it's the Navy,
science.
so it's that was my prize. And so I happened to live in the state of Utah when I was in high school, or sophomore in high school. And so they sent me the letter and everything and said, we're going to pick you up at your airport and we're going to take you to San Diego, California for the Navy science cruise. I was terribly excited. I'd never been to California and I wanted to see what that was all about. So this airplane came. It was not a jet. It had propellers.
Okay.
It didn't go real high and fast like a jet, but it was a big plane. And so it came and it landed, and they escorted me onto the plane. We got in there, and it was just all open and back. You could see the outside walls, and it was just a big open thing. They could carry cargo and things in it. And along both sides of the outside, there were these little seats. You pull it down and sit on it, do up a seat belt. And when I loaded up, the plane was already about half full of other Navy science cruise winners coming. So the plane had been hopping across the country, got there to pick me up, and we went on. It was one of those planes that, you know, it's not high. Bill Lear said, we need to be able to fly above the weather, up where the air is smooth, and up where you can go fast. Did you know that in an airplane, there is a tube? It's not big like this. It's a little tube. It's about the size of a pencil. But it's a tube that has a little teeny hole in it, and it points forward. It's located underneath the wings, called a pitot tube. Not a torpedo, but a pitot tube. And as the airplane's flying, it puts pressure on this little tube, and it measures how much pressure it has, and that's what tells the pilot how fast they're flying.
By the pressure.
By the air pressure on that tube. And of course, there are things that you have to do to correct that, like when you're up higher, it changes. Here is an interesting thing. If you have an airplane that is flying at 300 miles an hour at near sea level, you look at the pressure on the pitot tube and it tells you you're going 300 miles an hour. That's called the indicated airspeed. Why don't they just call it airspeed? And the answer is because how fast you're actually going will register differently depending on the air pressure. Like if there's a storm coming in, high barometric pressure, low barometric pressure, the indicated speed will change. And if you go up in altitude to where the air gets thinner, it doesn't seem like you're going so fast according to the pitot tube because there's not as much air to put pressure on it. And what I'm trying to say is, if you're traveling at 300 miles an hour at sea level, if you go up to, let's say, 40,000 feet or 30,000 feet and have that same indicated speed, you're going much, much, much faster. And that's how planes really go fast, is they get that high altitude. And that's why jets go up so high. And you know, how high do jets go? Well, they go way up there. A typical altitude for a jet flight is around 40,000 feet, or flight level 40. That's way up there. But did you know that where they fly is almost the height of Mount Everest? We have a mountain almost that high. That's shocking. The tallest mountain in the U.S. is about 14,000 feet above sea level. And if you put that next to Mount Everest, it's not even half the height of that mountain. It's kind of exciting,
It's very
isn't it?
exciting.
All right, well, coming back. So when they get up high, they can really go fast. When they're down low, they go slow. We were down low, so we were going kind of slow. And down low, you get the air rising. Did you know that there is a phenomenon where the sun will heat up the ground, like especially in the desert, and then a bubble of warm air will float up like a hot air balloon, and it creates turbulence for these planes. So we were flying across the Nevada desert and the Arizona desert, and it got pretty bumpy. And a lot of guys were getting sick, air sick, because and we had a lot of those.
Barf bags. Oh.
I didn't think we could say that. Can you edit that out of the Yeah, those. And it was after a whole bunch of them. When someone loses their dinner in these little bags on these airplanes, it smells. It kind of has this pleasant, not so pleasant smell. Okay?
It's a rank smell.
And when you smell that and you're bouncing around too, it makes you sick. And so everybody started filling their little bags. And
oh, goodness.
it was quite a flight. This is a Navy science cruise. So a lot of the kids on this, you know, some of them were seniors, juniors. I was one of the youngest ones, but some of them were really smart.
Yeah.
And they started figuring things out, and they started getting us organized. So we're big, empty airplane, guys strapped along both sides. We're flying along, and we have these Navy pilots up in front, you know, doing their steering. And so one of the guys says, "Okay, everybody, come on, come on." So we all got up, and he said, "Okay, we're now going to, two at a time, go to the tail of the airplane."
That's naughty.
Two at a time. So they walk down there. Now the pilot's there holding the plane level, but if you get weight in the tail, it wants to go nose up. Now two more, two more, and pretty soon we had everyone in the tail of the airplane.
You're a bunch of rascals, what
and
you
the
are.
pilots, this plane keeps wanting to nose up, nose up. And then on a signal, we all ran forward together.
Oh, goodness, guys.
And pointed. Then the pilot figured out what was happening.
Good pilot.
And then the plane went, and we went, and it was a lot of fun. Anyway, that has nothing to do with the story. Absolutely.
It's part of the best story, though.
Yeah, it's nothing to do with the story, but that was the Navy science cruise. Well, at any rate, when we were at Point Mugu, which is a research base for the United States Navy, they were showing us a lot of very interesting technology. They had a heat-seeking guided missile. Heat-seeking, that means if it can see the exhaust of an airplane, it'll fly towards it. So it would steer itself. And they had one of these mounted in a hanger so that it had a motor on it so it could swivel. And it had this little nose that was heat sinking, and it was so sensitive it could see our infrared emission from our body.
Wow.
So we went into the room, and it said, okay, and it turned around, so it was pointing right at me. It says, go over there. I go over there, and it'd turn with me. And it would heat sink back and forth. It was...
Kind of brings it right home, doesn't it?
It was really interesting technology. But then we went into the next lab, and I learned something really interesting. In that lab, they were designing antennas for radio waves, different frequencies, radio waves. And I was very interested in that because I was a ham radio operator, and they had some really neat antennas. And so I started asking questions, so how do you know exactly how to build the shape of those? And this scientist, very brilliant person that he was, made this interesting comment. He said that this room is a Fairchild cage. It's
Faraday cage?
Faraday cage. It's all blocked off. And so we have as little interference in here as possible, and we test these different things. They had sensors all around the ceiling. And he said, because with our current understanding, designing an antenna is less about science and more about art.
Really?
We try it, and we try it. So we can't understand why some things work. Now, that was years ago, but it's fascinating that an artist will draw a beautiful diagram out of feeling. A scientist's going to calculate the curves, take the derivative, and do it, you know.
Yeah.
Well, very often invention involves some art and it involves some science. And that's kind of the way these things are. So we want to send a message far away.
Okay.
Someone has said there's a thing called radio waves, and then someone else proved that they did exist. And so now we want to see if we can figure out how to send information from where we are to someone else at a distance. And we don't know how far we can go, but we hope someday we can go a long ways. How will we do it? And we want to take that step by step. Now, the Leyden jar is charged up with electricity and has a wire over to this little ball or little cup full of aluminum balls.
Okay.
And we want to see if when there's a radio wave, if these balls will conduct electricity.
Okay.
Okay? And if the radio waves will make them do that, we would have a way of being able to detect when there's a radio wave.
How are you going to do that?
Stay tuned. Stay tuned.
Okay, I will.
But step by step by step by step by step, it's these little teeny steps that we do. And you know, it seems like technology advances much faster when you have more people working on it. So it's kind of like competition.
It is, definitely.
And that's even true in art. If you look at the great composers, you look at the great artists, very, very often they were inspired by each other. And that's why classical music got better and better. It's why classical art got better and better. They were inspired by the work of others. And that's how scientists work.
It's neat.
So stay tuned.
Yeah.
The principles of how we go about analyzing the data, verifying whether or not our hypothesis or our theory is correct with experiments, that whole process is called the scientific method. It's an organized way of getting your thoughts and your observations down so that you can figure out what's really happening. And that's what scientists are trying to do. They're trying to figure out what's really going on. Right now, we're trying to figure out what happened to the Big Bang.
Yeah, was there really one?
There was a Big Bang, it's where everything started, but now we're not sure.
Yeah.
And there's dark energy because everything's accelerating apart, but we're not sure.
Now it's the Bang Big.
Now it's the Bang Big, yeah. So it'll be really exciting to see how this all works out.
Really will.
Maybe we should let her take just a few minutes and share with you some of her wisdom. Now, seriously, she told me something today that was just discovered that I think we all need to hear because it's something that I have discovered myself, but now there's a paper on it.
Yeah.
And they're saying that there is a way that we can be fulfilled, healthier, and happier. And I want everybody to hear about it. She was telling me about this before we started today, and I want you to hear it.
Well, I was wanting to be a little more ready, but how about I just give you a teaser?
Give me a teaser.
Okay. Gratitude. We all know we're supposed to be thankful. It's ironic that tomorrow's Thanksgiving, right? So we're talking about gratitude. But gratitude reshapes the brain, and it enhances brain regions linked to self-control and emotional regulation, helping you bounce back from stress and adversity.
Why don't you tell us in your own words? We're not following all that.
So when you're grateful, it literally...
Grateful for what?
Grateful for life, grateful for friends, grateful for health, grateful for
Bah,
food,
humbug.
grateful for people who challenge you. Seriously. Grateful for the ups and for the downs.
I'm a challenger.
But when you are grateful, and it's not just being happy, it's going through life and realizing you have so much to give thanks over.
Oh, I get it. So you're saying that on this side over here, you have self-pity, and
Yes.
on this side over here,
can I
you
go
have
there?
gratitude.
I didn't know I could go
Gratitude and self-pity. I feel sorry for myself. I'm grateful for what I
Yes.
have.
Yeah.
And you know, the famous story is the glass half full of water. Over here, half my water's gone. Over here, say, oh, look, it's still half full. It's an attitude of life. And as we go into Thanksgiving, I think we should focus on becoming grateful.
Yeah.
Grateful for our parents, grateful for everything, grateful for our challenges, our problems. If something bad happens, grateful for the lesson.
Right.
It really does change life. It changes health. It changes happiness. I mean, we have much. Go ahead.
I was going to say, and there's always something to be grateful for. You can always
Like
find
what?
something.
Like what?
Science life.
Yes. And on that note, we have news coming in from Area 51.
Okay,
today.
here it
he is.
Toot, 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 toot.
Well, hello, guys. It's Science Lifetime, and my name is Dr. R51.
Doctor.
Not really, but someday I'm going to be Dr. R51, but today I'm just plain old R51. But you know why I'm going to be doctor? Because I made a big invention. It's a really, really big invention. Do you see what this is? This is how you send messages, and I'm going to teach you code 51. This is better than Morse code. Now listen to this. This is A. Boop, boop. Did you hear that? That was A. It was da, da. That's A. Now I'm going to teach you the letter B in code 51. This is the letter B. Da, da. Did you get it? That's me. Want to learn C? This is C. Da, da. Now you know A, B, and C. Can you guess what D is? D is da, da, R51. That's not a code. All of the letters are the very same thing. You can't send any information that way. Well, yes, I can. I can send all the information I want that way because, do you know why? Because I'm special. So I'm going to teach you the letter E. Da, da. And here's F. Da, da. R51. You have to have every character be something different if you're going to do like Morse code. Everyone has to have a different code. I know that. You're speaking to a super intelligent being. Okay, I just invented code 51 version 2, and it goes like this. Now pay attention. Here is A. Da. Okay? Now here is B. Pay attention because it's different. So you can tell, is it A, is it B? This is B. Da, da. Did you get it? So here's A. Da. Here's B. Da, da. Do you get it? They're all different. And here's C. Da, da, da. And here's D. Da, 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 da. Here is E. Da, 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 da. And you want to hear Z? Here is Z. Da, 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 da. R51, you can't do all does. You're going to make the code so crazy. It'd be 26 does for a Z. You'd never be able to send a message. You have to have a code with some shorts and some longs. A is da-da. B is da-di-di-dit. You need to learn Morse code. Ladies and gentlemen, boys and girls, I'm now going to teach you the Morse code. Here is the letter A. According to Mr. Morse, he was a very brilliant person. Here is A. Dit-da. Did you get it? That's A. Dit-da. Now I'm going to teach you the letter B in Morse code. Oh yeah, here it is. Da, dit, dit, dit. Did you get it? That was B. Da, dit, dit, dit. And here is a C. C is da, dit, da, dit. Great, now we know A, B, C. You want to know D? Here's D. Da, dit, dit. And now I'm going to teach you the most important characters of all. You need to memorize these. Can you count them? 1, 2, 3. If you can count to 3, then you can learn these. This is S. Dit, dit, dit. Did it? 1, 2, 3. Dit, dit, dit. This is O. Da, da, da. See, it's 3. What if you're in trouble and you have to send out a distress message? You send a SOS, SOS. That stands for Save Our Ship, our spaceship, of course. Save our ship. So you send an SOS, you go like this. Dit, dit, dit. Da, da, da. Dit, dit, dit. If you hear that code, somebody really needs to. Now we know Morse code. I'm so glad we do this.
Breaking news! A UFO has been spotted hovering over IST. Witnesses say it appeared moments after a distress signal was transmitted. The SOS seems to have originated at the Area 51 laboratory.
All right. He caused us more trouble, doesn't he?
That's good. Wow.
Well, it is exciting for me to be on this great adventure with you. It's you remember that airplane that Dr. John showed us?
Yes.
The one with the oversized nose? That airplane must be an airplane where the pilot has to lay down. Remember, he said there's no windows to see out.
Right.
So he has to lay down to fly it. Do you know why I know?
Why? How do you know?
Well, it was the nose.
Wait, that's what.
Yeah, it has a really long Pinocchio nose.
Oh my goodness.
So it was lying down.
Wow, guys.
Anyway, we're going to have a lot of fun learning
very clever,
about
isn't he?
Inventioneering. But like that airplane, when it was ready to take off, it was sitting there on the runway. That's where we are right now.
Okay.
Fired up the engines. It started accelerating, accelerating, accelerating. We're going to do that. We're going to go through. We're going to invent radio. We're going to send a message. We're going to do. And as we lift off, all of a sudden you're going to say, oh, that's easy. I could do that inventioneering stuff. And you're going to start inventing all sorts of things. And the world will be better because of us. See you next time. Bye-bye.